We share
facts within the scope of applied mathematics.
It is all about understanding facts and sharing with others.
Learning continues. We are learning to know, understand, and share with others. Please subscribe to our channel if you like our videos.
Everyone, you are welcome to the third part of MTS 104. So, in this third part, I would like to solve more examples on curvilinear motion. And at the same time, I will introduce you to kinematics, where we are going to solve some problems. And don't forget, what is the difference between curvilinear and kinematics? In curvilinear, we need 2 or 3 dimensions. Curvilinear is actually for 2 and 3 dimensions. That is why we use the concept of vector. But in kinematics, we don't need that because it's actually a one-dimensional problem. So you are welcome. So like I've said, this third part is also 10 pages, as you can see here now, 10 pages. So let's start. The first question we are going to consider now, that's page 21, example 4. The question says, if a particle moves on a circle according to the equations, now x is r cos omega t, y is r sin omega t. Now we are asked to show that its speed is omega r. Look at that question. We are asked to show that its speed is omega r. Now, if you look at this question now, it means that we already have the 2 components of the position of the particles, of the particle. We already know the position of the particle. So let's continue now. Velocity along x direction. Don't forget that x here is talking about the displacement. Okay, so we differentiate the displacement with respect to t, then we have minus omega r sine. Don't forget, I've told you that you should go and practice how to differentiate simple functions like exponential, sine, cos, tan, sec, and other functions. Please take note of that, it's very important. So if you differentiate cos, omega t, don't forget that if you differentiate this, you return to sine, then you differentiate this, what is inside. If you differentiate omega t with respect to t, you have omega, then omega will multiply this. So you have minus omega r sine omega t. Now, velocity vector along y direction. This one means that we need to differentiate y. That is the component, the position component along, that is ij, that is along j direction. So we have this to be omega r cos omega t. Now, don't forget that the speed here is talking about the magnitude of the velocity. I've said it before, okay? So now, how do we get the magnitude now? That means that we use the formula which say that the square root of the velocity along x squared along y squared, then we find the square root. So look at it now, we have square root of what we have here, that is minus omega r sine omega t is squared, plus what we have here, that is omega r cos omega t is squared. Then let's take it in. Then in this case, minus omega r will take its own square, sine omega t will also take its own square. So we have, and likewise here too, omega r will take its own square, cos omega t will take its own square. So we have this. So we can factorize omega square r square out to give us this. Then we have sine square omega t plus cos square omega t. Do you remember trigonometry that the square of this is equal to what? 1. So if you replace 1 with 1, you now have square root of omega square r squared. So if you find the square root of this, you have omega r. That is how to show. You can answer now that the question is very wonderful, it's very simple. We are only asked to show that the speed is omega r. And what is the speed? Absolute value of the velocity. So let's go to the second question now. Now this time around, now this question now has to do with relative velocity. Let me explain what it means by relative velocity. Let's say we have 2 cars moving. Don't forget that both of them are moving. Let's say we have Benku A and Benku B, and both of them are moving. Then don't forget that it's possible for us to have what is called the relative velocity of one Benku with respect to the other. Yes, it's very possible. It's very simple. We only need to find the difference between the velocity. For instance, now I'm driving my car now, Big Daddy, with the velocity of 15 meters per second. I'm moving with the velocity of meters per second. Another person, a car beside me now. Let's say we are moving on a smooth surface that it can occupy 2 cars now. I'm driving my own Big Daddy with at the velocity of 15 meters per second, and the car next to me is driving his own at the velocity of 20 meters per second. And the question is this: what is the relative velocity of the car B with respect to Dr. Animasha's car. You know, in that case now, you're having the difference, and the difference is 5 meters per second. So you can answer it's very simple. So it's very simple, seriously. You just need to find the velocity of the two, then you subtract. You know, don't forget that we are saying car, let's say my own is car A, and that person is car B. So by the time you are talking about relative velocity, then you are talking about relative velocity of car B with respect to it. That means that the velocity of car B minus the velocity of car A. So let's take a look at this question now. That's example 5. We have two particles. They have position vector given by this. This is the position vector of particle A. This is the position vector of particle B. Now the question is, what is the relative velocity of the second particle with respect to the first at the instant of where t is 2? Now look at this now. We are asking that what is the relative velocity of this one with respect to this. So which means that we need to differentiate this with respect to t minus the derivative of this one too with respect to t. So look at this in your lecture notes. You see something I said, a question on relative velocity and acceleration is just the same procedure. You will get it. Any question you see, you solve, you get it. So let's solve it now. We have the first velocity now, the first particle. Let's define velocity. We have this. Then we evaluate at t equals to. Don't forget that we are looking for the relative velocity of particle B with respect to particle A. So we have this to be this. So by the time you change ct here to be 2, you know, we are evaluating the velocity of the particle at time t equals to 2. So we have this expression. So let's proceed again and do for the second again. We differentiate the position vector of second particle with respect to t. Then we have, then at t equals to 2, then you have this. Now relative velocity of particle 2 with respect to particle 1 will now be this one minus this. Then that will give us, don't forget that by the time you say minus, minus will multiply this, minus multiply this, will multiply this, then you have this. So by the time you say 8 minus 2, you have 6. Then 12 plus 4, you have 16. Then minus 3 minus 8 will give you minus 11. This is the relative velocity. Now what about acceleration? It's also the same thing. You differentiate again the second time. Then you have this, you have, then you evaluate at t equals to 2. Then you have, then what is relative acceleration? You subtract this minus this. So that will give us what we are looking for. Now let's go to example 6 now. We have a particle of mass m. It moves in the xy plane. Even look at its xy plane, that's 2 dimensions. So that its position vector is r cos omega ti plus b sin omega tj, where a, b, and omega are positive constants, and a is greater than b. Look at this question. This a here is greater than b. Show that the particle moves in an ellipse. Now remember, what do you know about ellipse? Ellipse is this. Let me remind you of the question of ellipse, about ellipse. That is x squared over a squared plus y squared over b squared is equals to 1. That is the question of an ellipse. And don't forget that we have 4 cases. That is, if the ellipse has the origin 0, 0, if the ellipse is horizontal and it has the origin of 0, 0, that's case 1. Case 2 is when we have the origin but the ellipse is vertical. The third case is when we have the ellipse that is vertical but the origin is h, k. The fourth case is when we have the ellipse, it is vertical but the center is not as 0, 0. That means that the center is h, k. Now if you remember all these 4 cases now, you will now notice that we can see the reason why they specify the condition that a is greater than b. You can see that. Now we are now asked to show in this question that this particle moves along ellipse. Now let's start now. We have the position vector now, which is xi plus yj, 2 dimension. Then we have this. And so we have x to be a cos omega t and we have y to be b sin omega t, which are the parametric equation of an ellipse, having the semi-major and semi-minor axis of length a and length b. Don't forget, a is greater than b. Now look at the equation I was talking about now. This is an equation of an ellipse. Now look at it, x squared over a squared plus y squared over b squared. In this case now, the ellipse is horizontal and the major axis is a, because a is greater than b. So we now have it to be, if you put x here now, you square, you have this. Do you know that if it, by the time you square this cos square omega t plus sin square omega t, we give you 1, then we have it to be 1. Do you know? We are true. It's very simple. So the ellipse is also given by this. Now let's go to the next question, page 23. A particle moves so that its position is given by r equals to cos omega t I plus sin omega t j, where omega is a constant. We are asked to show that the velocity v of the particle is perpendicular to the position. Wow, this question is very simple. See, how do we know that the velocity of the particle is perpendicular to the position? All we need to do is just to find the dot product. If the dot product is 0, then that is the case. If the dot product is 0, then that means that the velocity of the particle is perpendicular to the position. Now let's go. Now let's first of all find the velocity. Now you differentiate this one with respect to t to give us the velocity. Then we have this. Now let's find the dot product. Now if you find the dot product, you see something like this. This is the velocity. This is the position. Then let's multiply this and this, this and this and this. Then we have this expression. Of course, don't forget now, component of I multiply component of I. Don't forget that component of I, if it multiply component of j, ij will give you 0. Aha. So in that case, you don't have to do it like expansion of x plus y over in the bracket x plus y. No, in that case, you have it to be x squared plus 2xy plus y squared. That is x squared plus 2xy plus y squared. You don't have to do it because you know that ij and ji will give you 0. So let's only focus on ijj. So we have this. So this, and if you do this, you now notice that this and this, they are the same. So when they are the same, they can be given 0. Then if the velocity, if the dot product of the velocity and position is 0, then that means that both the velocity and the position, they are perpendicular to one another. So let's look at this assignment. A particle moves along the space curve defined by x equals exponential minus t cos t, y equals exponential minus t sin t, and z equals to minus t. We are asked to find the magnitude of the velocity. If you work it, this will be your velocity of this is the magnitude of the velocity. Do you know how to do that? That is square root, open bracket, the x dt in the bracket square plus the y dt in the bracket square plus the z dt in the bracket square. Then you find the square root, then you find this to be your answer. You also asked to find the magnitude of the acceleration. You do it like that, so you get it. So let's look at this assignment number 2 again. The position vector of two particles are given as this. Find the relative velocity of the second particle with respect to the first at t equals to 1. I think you can do it. You differentiate this at the first time, then you evaluate at t equals to 1. You differentiate it once, you evaluate at t equals to 1, then you say the velocity of the second particle minus velocity of the first particle, then you get the answer. I have the answer here. Then for the acceleration, you differentiate twice, then you evaluate at t equals to 1, you differentiate the other one, then you now say the r2 dt minus d square r1 dt square. Then you do it like that. Now that is the end of all the examples we have here under curvilinear motion. So you can see now that all the examples we've been solving from part 2 to part 3, all of them they have to do with 2 or 3 dimensions. So that is the end. Now let's go to kinematic, rectilinear kinematic. In this rectilinear, we shall focus strictly on one dimension. All the problems we'll be solving here are on one dimension. So let's start the journey. Example 1, page 24. There's a particular car. Oh, I didn't draw it for you. Oh, sorry. The car moves in a straight line such that for a short time, its velocity is this. There's just a car moving in a straight line, and you know, like I've said, rectilinear is one dimension. Then this is the velocity of the car. We're asked to determine the position and acceleration when time is 2 seconds. Note that from this case, we learned that the car starts from rest. So that means that at the initial time, we can have this. So let's go ahead and solve it now. Since the velocity is a function of t, that means that our velocity is derivative of position with respect to time. So we have it like this. So you know I can say ds, the s can stand here, the t can come to the other side here. Now we need to integrate from 0 to x, 0 to t. Why do we need to integrate? Don't forget that the particle is at rest. So at rest, it means that the initial time is 0. Then the upper time is what varies that we don't know. So we have the t. And don't forget, at the initial time, the position is also 0. So that's why we have 0 here. Then the final position is what we don't know. It varies. That's why we have 0 to x, 0 to t. So if you integrate 0 to x, you know you have x. You evaluate from 0 to x, then you have x minus 0, then you have your x. If you integrate this one, you have this, then you have this. So let's evaluate. Of course, don't forget, like I'm saying, if you have to integrate polynomial, that will be what? You add 1 to 2, then you divide it. That will be 3t, 2 plus 1 over 2 plus 1. And 2 plus 1 is 3. 3 will cancel this 3, then it will go. This one too, you know, we have 1 plus 1, that's squared, then over 2 we cancel, so then you have this. So you evaluate from 0 to 2 because at the initial time you have 0, at the upper time we don't know, vary. So you have this. So when t is 3 seconds now, so you evaluate the position at 3 seconds, then you cannot say that if this is the velocity of the particle, then if the velocity of the car, then at time 3 seconds, the car should be at 36 meters away from the origin. Now we're asked to also find the acceleration. How do we find the acceleration now? We differentiate the velocity once. So this is how we can see here. We say ddt of the velocity. Then this will give us, you know, we are differentiating now. You have 6t plus 2. Now at time t equals to 3 seconds, then you evaluate the acceleration at 3 seconds. Then you have 20 meters per second. So which is that at exactly 3 seconds after the motion, then it means that the acceleration is 20 meters per second square. Now there's a note here. Remark, note that the formula for constant acceleration cannot be used to solve this problem because the acceleration is a function of time. Look at what I'm saying. See, all the Newton's law of motion, they stand on the fact that the acceleration is constant. Please let me say it again. I can even ask you this question in your test, that what is the limitation of Newton's law of motion? One of the limitations is that acceleration must be constant. And in this space now, we cannot use the concept of Newton's law of motion because here you can see now that the acceleration is changing. It's just like someone that is driving and you put your leg on the accelerator and you are pressing it small. You know, as you are pressing it, the velocity will be changing. And if the velocity is changing, then Newton's law of motion is not applicable here. Can you now see the advantage of rectilinear motion now? You know, we can't solve all the problems, all the dynamics using Newton's law of motion. We can't. We cannot. So that is why we need to use this concept of one-dimensional rectilinear motion. Because when the acceleration is changing, then this approach is the best. But how do we get the function for the velocity? It's very simple. In my tutorial group, I mentioned to them that we can use the concept of interpolation. When we know as time is changing, you know the velocity of the particle, then we can convert the data to a function using the concept of polynomial, using the concept of interpolation. So when we have the velocity, then we can deal with it. We can use it to do anything we want. Let's go to page 25 now. Example, the distance x meters moved by a car in a time t seconds is given by this. This is polynomial again of order 3. Now we're asked to find the velocity and acceleration at the initial time at time 1.5 seconds. Now let's go. We have the distance. How do you get the velocity? We differentiate once. Then you have this. How do you get the acceleration? You differentiate the velocity once, or you differentiate the distance twice. Then you have this. Don't forget the unit. You know I'm saying it too. I may give you some questions. I will put unit. Some I may not put the unit. And if you pick the answer without unit, I'm telling you, you won't get it right. Because this is dynamics. We need to deal. We are all science students, and we have to speak the correct language. So that is why we need the unit. Now, when t is 0, you put t in the velocity, then you evaluate. You see that t here you have 4. When acceleration is 0, you put here, you have minus 4 meters per second. Now, let me ask you this question. Is technical. Can we use Newton's law of motion to solve a problem like this? No, because the acceleration changes with time. We can't. So because of that, now that is how to solve that. Let's go to page 26. Now we're asked to consider the displacement of a particle, which is this, a polynomial again, at t equals to 2. We are asked to find the displacement, velocity, and acceleration. Now we are not asked to use the information above to say something on the maximum velocity. That is another thing about rectilinear kinematics. It's very sweet. You know, it can give us this kind of graphical illustration. Remember I said it earlier that the concept of Newton's law of motion is based on the fact that Isaac Newton can really use the knowledge of calculus. So we're going to use the same concept too, to obtain maximum velocity. Yes, we will know when the velocity will reach the maximum using this expression. So at time t equals to 4, we're asked to obtain the displacement, velocity, and acceleration again. Let's solve the problem now. Solution. This is the position vector now. Oh, don't let me call position vector now. I'm just talking about displacement. Oh, so if it's a displacement, then it means that the velocity, we are dealing with velocity now, not speed. So if you differentiate once, you have 12t minus 3t squared. Don't forget how to differentiate simple polynomial function. You know now, 2 minus 1. Then you multiply 2 by 6. 3 minus 1. Then you multiply 3 by the coefficient here. Now, what about the acceleration? Now, let's go now. At t equals to 2 seconds, let's evaluate the velocity. Let's evaluate the position. Even let's start from the position vector. From the displacement. If you evaluate this one at t equals to 2, you have 16 meters. If you evaluate velocity at t equals to 2, you have 12 meters per second. If you evaluate acceleration at 2 seconds, you have 0 meters per second. What does that mean? It means that acceleration is a constant function. So for this example now, we can use Newton law of motion. We can use it. We can use it to further explore the problem. Now let's try to plot a particular graph. Look at this graph now. This is the displacement time graph now. From the function, I can have something like this. Now, what about the velocity? I can plot the graph of the velocity like this. I only consider time to varies from 0 to 6 about this. Now, look at this graph. You will notice that the velocity is increasing, But at time t equals to 2, there was a kind of turning point. Then the velocity starts decreasing. Can you not see the reason why we need to call this one displacement? If I should give you a program like this, and we have it like this, you cannot see that because we have a negative velocity. Because we have a negative velocity, it means that we are actually dealing with the displacement, not distance. So if you look at it, you cannot see that there will be a maximum velocity at time t equals to seconds. That is why they said that here, use the information above to remark on maximum velocity. So we can see that at t equals to 2, we can see the maximum velocity here. Now let's proceed again. The graph of acceleration, look at the graph of acceleration now. A simple straight line graph. You can see, what is the slope of this straight line now? The slope is what? Who can tell me the slope? The slope now is that, the slope is what? -6. Look at it. The slope of that line is -6. The slope of acceleration time graph is -6. Minus means that the negative value. And don't forget, I've said it before, that when the slope is 0, it means that there's no relationship between the two variables. But when the slope is negative, it means that there's a decreasing relationship. If the slope is positive, it means that there's an increasing relationship. So we have it like this. Now you can see that the decreasing relationship now, that as the time is growing large, the acceleration is decreasing. Now note that B maximum occurs when A is 0, and that the slope of the velocity curve is 0 at this point. Look at it now. This is what I'm saying now. At t equals to 2 in the velocity, you know that here, this is the maximum velocity. Here, the velocity is 0. Look at 2 again. The acceleration is also 0. Can you see that the concept is very accurate? Now, the second question is very simple. You don't only need to evaluate at 4 again. Let's go to page 27 now. A particle starts from rest. Now, what does that mean from rest? It means that at t equals to 0, the position is also 0. That is the meaning. With an acceleration of 10 minus 2t meter per second squared. At any time t, when and where will it come to rest again? You know, I was saying it at the beginning of this. I said this knowledge can help us to determine the missing, to resolve the case of missing aircraft. The last time the aircraft contacted the aerodrome, we learned that the acceleration of that particle can be given as this. Do you know how we come up with this? We only need to get the acceleration at subsequent time. Let's say at different 5 times now. Then if you have a table, you have times, we have the acceleration, we can convert that to a function using the concept of interpolation. I've said it, I'll say it again. That is the beauty of mathematics. You know, don't forget what we are studying. We are studying introductory to applied mathematics. So you can understand that if we have the data of time, acceleration, let's say when time is 1, that is when the aircraft is closer to a particular aerodrome, a particular airport, or a particular space charge. Airport rather, thank you. You know, at time t1, we know the acceleration. At time t2, we know the acceleration. At time t3, we know the acceleration. At time t4, because in fact, with that 4 data, we can use to come up with this function. So let's proceed now. We are asked to find when and where. Now, even the case of launching aircraft, the launching rockets now, this is also important. You know, we are saying when and where. You know, we are asked to find 2 things now. Okay, when it comes to rest again. Now let's start. We have the acceleration. From the acceleration means that you differentiate the velocity with respect to time. So we have this acceleration. Then, if you need the velocity from acceleration, what will you do? You integrate. So if you integrate 10 minus 2t, then you have this. Then that means that velocity is what? Look at it now. If you have to integrate 10, what will you have? 10t. If you have to integrate 2t. What we have 2t squared over 2. Then don't forget constant of integration, c1. But the particles start from rest. If the particles start from rest, it means that at t equals 0, the displacement is 0, velocity is also 0. So we have this expression, at t equals 0, we have the velocity to be 0. Now let's substitute this into d so that we can find the constant of the integration. So when b is 0, now look at the b is 0, then you set the time t equals to 0, then you set t equals 0, then you can find your c. And you see that even the constant of integration is 0. So you return it 0 back, then you find your velocity. Now, we can't stop here because we need to find. Okay, now let me first of all find the body is at rest when v is 0. You know, when do we say body is at rest? When the velocity is 0. So when velocity is 0 here now, we are trying to solve the problem when. So we have the 0, then we have 10t minus t squared. When it's talking about time. So if t minus t squared 10t is 0, then we can multiply both sides by minus, because if you are solving the quadratic, the coefficient of the highest order should not be negative, make it positive, so we can multiply both sides. So we solve this one quadratically, you will see that t is 0 and t is 10 seconds. So which means that you can now say from this one that the particles start from t equals to 0. Then at time t 10 seconds, that is when the particle will be at rest. Because when the velocity is 0, we see that the t is 10 seconds. Now let's proceed now. If x is the distance traveled, then velocity is ds dt. So we have this. I'm using this expression here. Because velocity is the x dt. So you now make the x dt, then you have the t, and then you have this. Then what next? You integrate. When you integrate both sides, you have 10t squared minus 1 over 3 10t raised to 10 plus d. Here, d is the constant of integration. So recall that if the particle is at rest, that's when t is 0, then displacement is 0, then velocity is also 0. So we can have this condition. Let's put the condition there, then you can find this is 0. So the question is this: at t equals to 10, that is when the particle will be at rest. Then let's try to find the displacement. So you put 10, t equals to 10 here now, then you find this to be your answer. So let's hurry up and go to the next question. We are still dealing with rectilinear kinematics. So page 28 of your lecture notes now. Supplies are drawn from a helicopter and the distance falling in a time t seconds given by x equals 1 over 2 gt squared, where g is 9.8 meters per second. Now, we asked to determine the velocity, and we are also asked to find the acceleration of the supplies after it has fallen for 2 seconds. So displacement is this. What is the velocity? You differentiate. You have 9.8 over 2 multiplied by 2 minus 1, then we have this expression. Then acceleration, you differentiate. Okay, again you can now see that the acceleration is 9.8 meters per second squared. Look at it in this problem now. It means that we are dealing with a constant acceleration body. It means that in this motion throughout, the acceleration is constant. The acceleration is the same thing. Even if you look at this expression, I think it looks familiar. Look at it very well. 1 over 2 gt squared is very familiar. It's one of the components of the equation derived by Sir Isaac Newton. So at t equals to 2 seconds now, then you evaluate this, then you find your answer. Now, next example now. The displacement in centimeter of the slide valve of an engine is given by this. Obtain the expression for the velocity. Here, you only need to differentiate once. And when you differentiate, then take note. I'm saying it again. How do you differentiate cause and sign? Go and learn. Practice so that you won't make mistake. We are only asked to find the expression. And here, you have the answer in centimeter. Do you know that we can convert this one to meter? What do we do? Go and learn how to do that. Then we can convert this one to meter. All we need to do is to change this one to meter. Then we multiply every day by something. Now, page 29, second to the last page. A small projectile is fixed vertically downward into a fluid medium with an initial velocity of 60 meters per second. Due to the drag resistance of the fluid, the projectile experiences a deceleration. Now, look at it. Just like you have a swimming pool and you want to jump inside it. The velocity at the surface of the water, if you know the velocity will be 60 meters per second, what do you think will happen to your body? As you are going down, we experience what is called deceleration. Yes, because of what is called thrust. Thrust is the force that tends to push all objects upward. And we have it inside water. The force is that's why if you are trying to fetch your water, maybe you drop the container inside the water, you will experience that when you are coming up with it, we are trying to draw it upward. You will just need to apply small force. Because there is already a force at the bottom of the water, at the bottom of the, we're trying to push it upward. But immediately you lift the bucket above water, you feel the weight. You feel the weight. So that is what this one is talking about. That we have a small projectile is fixed vertically downward. Then we know the initial velocity, we know the acceleration. The question is we have to determine the projectile's velocity and position 4 seconds after it's fixed. Look at this diagram now. This is the diagram now. We have the object now. Then you throw it inside water. This is the water body now. Then it explains deceleration of minus 0.4 meter v cube mx minus 2. Then how do you go that? Let's do now. Acceleration is a function of velocity. Now, since the equation relates velocity, acceleration, and time, we can start with this expression. Look at that. Look at that. Just because the problem tells us about velocity, it tells us about acceleration, and we also know time. What is the first thing? You do Newton's first law of motion. Now you see now that V equals of V naught plus AT. You're supposed to ask me that why did I come up with this? See, look at this expression. Do you notice that acceleration here is a constant function of time? Yes. If you look at this expression, t is not here. So let's proceed now. But V here is something. You will see what it means now. Let's proceed now. Let's first of all consider this now. We have, if you differentiate both sides of this one now, you differentiate this, you differentiate this, then the VDT, then you differentiate this, then you have V naught plus AT. So if you differentiate constant, so let's proceed now. So the VDT is now A, which is minus A 0.4 V cubed now. Now let's consider the two expressions now. So we are considering this and this, this and this. We are considering this and this. So what's next? The V will stand here, the T will come here, this one will come here. We are trying to separate the variable. So you know that we have dV, then we have minus 0.4 V3, we come under, then you integrate the T now. What do we need? You know that initial velocity was 60 meters per second. Then what about the final velocity? We don't know. That's why we write V. Initial time is what is 0. What about the final time? We don't know. So you put here. So now we need to integrate this expression. Now let me tell you something. You know this one is denominator. If this one should come up, you know the power is plus 3 before. If you change to minus 3. Now how do we integrate this now? Don't forget that, like I said, now you can answer that dA is talking about the velocity raised to power 3. So let's come back here now. So if you do that, minus 1 over 0.4 will come outside. So if you integrate this now, that's that minus 3 plus 2 will give minus 2. The minus 2 will come under. Don't forget integration, you divide. So you evaluate from 60 meters per second to V. Then if you integrate, you have T. Then you evaluate T to 0. So what do we get now here? We evaluate, you put the upper, you put the lower, then you subtract, you simplify, you still simplify, then you have this expression to be plus or minus. But we shall consider only the positive root since the projectile will continue to move downward. So we now have our velocity to be this. So we evaluate our T equals to 4 seconds. We have here, we put T to be 4 seconds here. So we evaluate, then we have the velocity 0.559 meters per second. Now let's proceed again. We still need to find the position. How do you find the position now? We need to consider the fact that the velocity is what? The x, the t. Now look at this. This is our velocity. Do you know what we've done here? This velocity here, we have this one to be our velocity now. And here, this expression to be our velocity, we can also express it to be like this. Because look at it, square root of 1 is 1. And this one here, you know, this is 1 raised to 1 over 2. If you move 1 over 2 up, it's 1 with minus 1 over 2. That's how we obtain this expression. So let's integrate. Remember that at the initial time, we don't know, initial time is 0, but we don't know the final time. What about any displacement? What about time? We know the initial time to be 0, we don't know the final time. So you integrate both sides. So when you integrate, you see that, then you have the displacement to be 4.43 meter. Thank you very much. Here we shall come to the end of the third part. So thank you very much. Like I've said earlier, it may only look voluminous, and I said the only reason why it's voluminous is because I would like to solve many questions so that you are familiar with what we are learning. Are you with me now? So that is the reason why it's voluminous, and I've said that it's only a lazy student that will complain. If you are not a lazy, even look at me that I'm recording it too. If I'm lazy, I won't have time for all this, so I will just look for time out of no time to try to teach you and also send videos across to you. So please, to whom much is given, much is expected. So I expect each and every one of you to look for time to pay attention, to read through line by line, practice. You can write the question and close it and solve it again. Maybe you get it right. Thank you very much. Thank you.
We share
facts within the scope of applied mathematics.
It is all about understanding facts and sharing with others.
Learning continues. We are learning to know, understand, and share with others. Please subscribe to our channel if you like our videos.